Good evening, everyone. So for the today's learning lecture, I would like to talk about data cleaning and pre-processing for model training and stuff. So actually, why we need pre-processing? Because so often the real world data is incomplete, inconsistent, and it's not in the state which can be used to train a model or to be used for any other statistical uh, analysis. So in that case, we need data pre-processing. So this is an essential step in transforming raw data into information, which can be used to uh, get conclusions and make decisions based on the information. And this increase the accuracy and reduce bias, and this is it makes it easier to train a model, and we can get meaningful insights from the data. So let's move on to the first, like what are the main phases or steps in data preprocessing. First, we have to clean the data, and then we have to integrate them, because like we get data from multiple sources, so we have to merge them and integrate them. Then we have data transformation and feature engineering and data reduction. So first, let's talk about data cleaning. So what is data cleaning? And like data cleaning has several, several applications. So one is we have to handle missing values. So missing values can skew analysis. Like when there are missing values, the dataset can be skewed into one direction, and it reduces the accuracy of the predictions made by the model. So we have several methods to handle missing data, but before that, I would like to tell that we have to choose the correct strategy, because let's say there's a situation that, so when we are analyzing the data, we have to think why this data is missing, because sometimes this data is not existing. Uh, like if a person is not married, or if a person doesn't have a child, then the age of the oldest kid is uh, not a valid answer to ask from him. So that missing value should be removed, not imputed, uh, because it's not an existing value for that entry. So likewise, we have to choose the method to handle the missing data. So first we go for the removal. So removal means just we remove the entries or the columns with too many missing values. But this cannot be used with datasets with a lot of missing values, because then the dataset will be reduced into smaller sizes. Uh, without removing a data entry, we can use imputation. Imputation means replacing a missing value with a selected value. Like we can use mean, median, mode, or just a constant to replace the missing value. Like a simple library called simple imputer from scikit-learn library. We can automatically use imputation without, like we don't have to manual write functions to imputation. And also we can use advanced techniques, like we can use another model to find the guess the missing value. We can enter the column information, column data into a KNN model or a regression model, and then predict the value for the missing value. But the problem here is it requires additional computation, but this way might be much more accurate than the previous two. Then move on to the handling duplicates. So why we need to handle duplicates? So having duplicates in a dataset can create skewness, because the multiple entries on the same value can create a huge stack on that value, and that can make the dataset skewed, and which make the predictions of the model biased into a wrong direction. And having the same entry multiple times require additional computation, and having duplicates can occur issues in merging data sets like data integration. So the solution is we can just remove the duplicates, right? So for as a simple solution, we can remove the duplicates. So now we replace the missing values and we remove the duplicates. Now we have to handle the inconsistencies. So when we are collecting data, let's say we are collecting data from an electronic form. So the way people enter values can be different. Like as an example, you can see uh, for the month, one person can enter Jan, or one person can enter January, the whole word. So these are the same. These are the two words with the same meaning, but they but a model considers these as two different values. So we have to merge these and remove the duplicate ones. Like in the second example, you can see it is about uh, the capital and simple letters and the white spaces at the beginning and end of the word. So we have to remove these inconsistencies in the data set. And when it comes to format, so especially in dates, like when it comes to time series analysis, dates and times are very important information we need to extract. So in such scenarios, we need to extract the relevant information from those given values. So for that, we need all those values in the same format. Like if you can see here, uh, these are two standard formats we use to write a date, uh, but we need to turn all these into same format. Otherwise, we can't use them on a training model. Uh, the other one is outliers. So in almost every case, when we are collecting data, we get outliers and we need to remove them. Otherwise, like these huge outliers can lead to wrong predictions. Like in a data set with a lot of outliers, and if the model is also overfitting, these the predictions can be get wrong. So these two are the like most widely used methods to handle outliers. The first one is IQR. So so IQR is the difference between the third quartile and the first quartile, like and for the data set, the lower bound will be Q1 minus 1.5 times IQR, and the upper bound will be Q3 plus 1.5 times IQR. This 1.5 is usually used value, like a standard value, and it can be different from the data set. We can use visualizations, and we can get this value. So any value out of this range will be considered as an outlier. So the score method, so we know the Z score, like we can calculate the mean and the standard deviation of a data set, and we can calculate the Z score for each value. And if the Z score of any of the data point is larger than above a threshold, then we consider it as an outlier. So usually we use a value between 2 to 3 because so for most of the data sets, the values with the Z score greater than 3 is less than 1%. So that should be the outliers, because uh, usually we have a few outliers considered to the size of the data set. So we can use these two methods to handle outliers from a data set. And the next topic is data transformation. So now we have removed the uh, inconsistencies and missing values from the dataset. Now we have to transform the dataset into a state which can be used to train a model or to get insightful information from the data. So let's talk about scaling. So what scaling does is it changes the range of the dataset. We can So the shape of the distribution or the distribution of the dataset is preserved while the range of the dataset is minimized or maximized uh, as as it is desired. So for machine learning methods like KNN or K-mean clustering or support vector machines, uh, the distance between data points or the Euclidean distance, and for KNN it might be the distance between the two vectors, the angle and the magnitude. So all these method, machine learning methods use the distance between data points to make decisions. So in such scenarios, and scaling is important. So this is the equation we can use, like x is the data point and minimum of x means the minimum of the data set and maximum of the data set minus minimum of the data set. So we can normalize the data set using scaling, and we have standardization as well. So the difference between scaling and standardization is in standardization, we change the both range and shape of the distribution. So what we are doing here is we change the data set into standard data set. I mean, a data set which takes the standard bell curve shape. So actually, here there's an issue like for machine learning methods. Yeah, here actually I should make this. So here the machine learning methods like Gaussian, naive Bayes, and other machine learning methods which use standardized data sets. We need standardization for such methods to be used. And so those are for the numerical data sets. So now we have categorical data. So for the categorical data sets, we have two encoding methods. One is label encoding. The other one is one-hit encoding. So let's consider a column, and there can be a lot of unique values. So if these unique values has an order, like here given in the example, if the unique values are low, medium, and high, we can map those three values to 1, 2, 3. So similarly, let's say if it is about often-ness, like if it is every day, if it is always it's 1, and if it is rare, it can be 7, and anything in between those two can be mapped into any other integer. So likewise, we can use label encoding. So here we just map these labels into a number, uh, considering its weight or the order in the given node. But let's say we have a data set and in a column we have categorical data, and these unique values doesn't have an order. So they are just nominal data. So now we don't have an order. We can't just map them into numerical values. So in such cases, we can use one-hot encoding. So in one-hot encoding, we create a separate column for each unique value or the label in the column. And so for newly created columns, we just uh, give two values like Boolean values if it is true or false. Here the problem is this cannot be used for columns with a lot of unique labels. Like if the number of unique labels exceeds maybe 15, maybe, yeah, 15. So then a lot of new columns will be created, and it takes a lot of time to train a model, and it make the computation hard. So when we are choosing encoding method, we have to think of such things. So next we have feature engineering. So feature engineering means when we are training a model, we need to find the relevant variables. We need to, like, we can connect them. So what are the variables dependent on other? Because when we are collecting data, we don't know. So we can visualize them and see what are the relevant variables and what are the connections or the relationships between those two variables. So feature engineering is to create such variables and figure out what are those variables. So and why it matters, because to get better predictions and for a accurate model, we need good features. And also, if we don't find the, like, let's say we have already the best dependent variables and also some other unrelevant variables. So when we are having unrelevant variables, it can make the predictions inaccurate, as well as it make the computation hard and make the process long. So feature engineering can both increase the accuracy and the performance of a model. So as an example, like you can see, uh, if it is a timestamp data set, so you are given the time for each entry, we can extract the type from the dataset. And especially, as I told you before, in time series data analysis, we need the time, the exact time, maybe the time, maybe the date. So we can find the cycles or seasons inside these uh, time series data. So in such cases, we need to extract those information from the timestamp. We can't just uh, train the model with the timestamp given. And we can, so yeah, so in some cases we can detect, like we can figure out some two variables, and sometimes a combination of those two variables will be a better feature which predicts the target value. And also we can see, like in LLM, so here it says converting text into numerical features. Sometimes they might be encoded, or sometimes we have to encode them. So in such cases, we need feature engineering. Even in LLMs, like we make chunks of a text. So that is also an example for an feature engineering. So like how to find out the relevant variables or the dependent variables. So mutual information is a way to find out what are the relevant variables or the dependent variables. So actually, the given below equation is one of the equation we can use to uh, find the mutual information. So when this mutual information value gets higher, it it says these two variables are dependent, or they have a stronger relationship and all. And if you can see, this value is always positive, and if this value gets zero, that means they are independent. Now let's assume that, so here you can see pxy is the joint probability. That means like the probability that x equals x and y equals y. So when the both happens, that is joint probability. And marginal probability means px means the probability of x being x, and py means the probability of y being y. So when the two variables x and y are independent, the pxy, the joint probability, can be written as px times py. So then this term gets 1, and log 2 to the power of log 2 1 equals 0, and this I, or the mutual information value for these two variables, gets 0. And when these two values are dependent, these values get higher. You can see this is a correlation between the two variables, and this is the mutual information heat map for a data set. So you can see these values are similar, like here between ROK and NSIT, two variables, there's a higher correlation. And even in the mutual information, the value is higher compared to the other values. So mutual, like we can find mutual information for all the variables given in a data set, and we can rank them in the order. Then we can pick the uh, the best pairs of variables to find the or to train the model to get the predictions from the model to the target value. So yeah, that's about the mutual information. So after getting this information, we can get the needed variables, and we can create the correct features for the data analysis. And now we have data reduction. So what is data reduction? So as I told you before, in one-hot encoding, lot of columns are created. Sometimes for as feature engineering, we create new variables or the new columns which will be used to predict accurate accurate target value. So this makes the dataset larger and larger. Like for each entry, we get a new value. So for if the values are represented as vectors, for each vector, the dimension will be increased by 1. Uh, So data reduction is after all these processes, if we find the data set is huge, we reduce the data set. So we have several options to do this. Actually, the first one is feature selection. So after the process of feature engineering, we find the best variables we need to predict the final value. So after we have stronger variables, we can pick those only for training. So then we can reduce the computational power we need for the uh, training a model, and also we can reduce the dimension. So that means we can transform features into fewer components. Like as we saw before, we can get the ratio of two variables, and we can get it to be one value. So then one dimension is reduced. For a huge data sets, we can get a sample which represent like all the entries given there. We can get a subset from the data set, and we can use that to train the model. So, but this is only for huge data sets. Otherwise, the predictions will get inaccurate. So using data reduction, we can reduce overfitting and also reduce the computational power needs to train a model. So that is data reduction. So with all these steps, we can have a better set of data to train a model and to get a better predictions. Yeah, so that's the end of my lecture. So thank you, everyone.